lecture will be on topology and geometry of n-norm spaces. Perhaps some of you have heard of these animals, n-norm spaces, which I learned from my colleague, Professor MYSAGA from Unri, 19 years ago, something like that, maybe 20 years ago. I have 5 lectures as I wrote in the abstract. I hope you already read the abstract from the website. The first lecture, which is given today, will be just introduction to the theory of n-norm spaces and also the counterparts and inner product spaces. So tomorrow I will talk about the topology on these spaces. Okay. Actually, I have the plan for tomorrow and also for the next day. So on the third day, I will talk about the orthogonality in n-norm spaces, which Hendra learned during her undergraduate study here 15 years ago. You graduated 14 years ago, but you learned about this 15 years ago. And on the fourth day, I will talk about angles within two subspaces of linear product spaces, and also on the fifth day. But on the fifth day, I will present something quite fresh, which I did at the end of last year when I visited Australia. I met Professor Wildberger there, and he also has a formula for angle between subspaces in Euclidean spaces, and then we compare the two formulas. Of course, they look different, but then the question was, are they actually identical? And then I did some calculation, and I figured out that his formula is also is the same as mine, but he used different language, more in matrix or linear algebra language. So I will come to that in on the fifth day. Okay, so basic assumptions now that I assume that everyone is familiar with the notion of norms and inner products. They are usually defined on vector space, and for simplicity, I will assume that our vector space is real. That means the field is R, real numbers. Okay, you can, if you like, you can do the complex version of what I talk. Assuming that you know the norm space, I will begin with the notion of two norm spaces. So here, the vector space X is at least of dimension 2. Okay, because we are going to talk about something geometrically related to the notion of area. So the dimension should be at least 2. So a 2 norm on X here is a function of 2 vectors. So it's on X cross X, satisfying the following 4 properties. So imagine you have 2 vectors X and Y, and imagine you have the parallelogram spanned by x and y. So by saying the parallelograms spanned by x and y, I mean this region. Okay. So from high school we know how to compute the area of the parallelogram is base times height, and to find the height you have to project the vector on the base and so on. And then you multiply the base and height. So the four properties here can be interpreted geometrically. So the first one says that the area is 0 if x and y are linearly dependent. That means if x and y have the same direction or reverse, the area is 0. Okay, so the h will be 0. And then the second one, the area spanned by x and y is the same as the area spanned by y and x, so it's invariant with respect to the order of the two vectors, so it doesn't change the value. And the third one says that if you multiply one vector by a scalar alpha, then the area will be multiplied by the modulus of alpha. Okay. So for example, here if you multiply by 1.5 size, then the area will be alpha times the original area. And the last one is the triangle inequality. So I guess you can write the you can imagine what happens if you have y and z, and then you think about the area spanned by x and y plus z compared to the area spanned by x and y and the area spanned by x and z. Okay, so if you think of y and z as the vector where you compute the height after projecting it to x, then of course you just use the triangle inequality for the length of y plus z compared to the length of y and the length of z. Okay, so with this property we have a two norm on x, and the pair x with this two norm is called a two norm space. So you can refer to this paper by Doppler in 1965. I remember I have a hard copy of this paper, but I don't know where it is now. So I hope you can find it somewhere online. It's an old paper in the journal, a German journal, Mathematics. But I guess a long time ago there were also papers by Menger or some other name, Menger maybe, discussing similar ideas. But we usually refer to this paper as the origin of the theory of two norm spaces, and then later on we generalize n norm spaces, generalize version of this. And then if x has at least 3 dimensions, then we can also have this mapping with these 4 properties, which is called the two inner product on x, and the pair is called two inner product spaces. I will explain why people come up with this function soon after this. But in this function, this is the notation that people normally use now. So in this notation, the first two factors on the left, they interact like in the inner product. So the function is bilinear in the first two factors. But the third factor is like a parameter here. It's like something which has a different role. So that's why we don't use comma here, but we use a vertical line. Yeah. What I will say here. Actually, this first expression is equivalent to norm actually. Later on, this will be recognized as a two norm square. Yeah. So here x and y are different, but in the first two, it's like x is equal to y, so we have this, and the value of this is non-negative, so it's like a two norm, and then it is 0 if and only if x and y are linearly independent. So this is like the first property of the two norm. Okay. Of course, now it's a bit maybe artificial, but I will explain this soon. Gahler with Charles Dimini and Albert White, I think, wrote about this two inner product spaces. First one and the second one, they published it in 1973 and 1977. So quite a long time ago also. So okay, I will explain like notice this is like why how two norm and the two inner products appear naturally, and then also the three norm and three inner product spaces and so on. So let us begin with the inner product space. So let us begin with the vector space X equipped with an inner product, and then we know that from the inner product we can have a norm given by this formula. So although I have assumed that you already know, but I need to present this just to see how things flow from this point. Okay? So given an inner product, we can define this function, and then we realize that that function defines a norm. Of course, we have to prove the property of the norms, and one of them is the triangle inequality, and that triangle inequality follows immediately from the Cauchy-Schwarz inequality, which is that inequality. Okay, so the question is, do we really have the Cauchy-Schwarz inequality? Of course, yes. And there are many ways to prove the Cauchy-Schwarz inequality. This is undergraduate stuff. But one way to prove the inequality is by rewriting it as a determinant inequality, which is this one. And this matrix is called Gram matrix of size 2 by 2. And we immediately see that the determinant is non-negative. Okay, so the Cauchy-Schwarz inequality holds since the matrix is positive symmetric. you see, you multiply this and then for the students, how to check the matrix is positive semi-definite. You multiply this by factor alpha beta, and then you multiply by that, and this will be, of course, you have to check. You have to do step by step, but at the end you will get this. Okay, so the inner product of alpha x plus beta y by itself, and this is of course negative, and it's true for all alpha and beta. So that's what I mean by positive semi-definite. Okay, and yeah, you get Cauchy-Schwarz inequality from this determinant for inequality. Now, one more thing about from this inequality is that we see that the equality holds if and only if x and y are linearly independent. So that result is very clear from this inequality. Why? Because if x and y are linearly independent, then you can do elementary row operation. Okay, so the second row will vanish after doing the elementary row operation. And conversely, if it is 0, then y must be a multiple of x. Okay, because of the property of determinants. Now, this is what is important from the inequality, what we see from the inequality. First, we know geometrically the ratio here is the cosine of the angle. Okay, we know that from maybe even from high school. But then soon, since the determinant is non-negative, we can take the square root, and that square root we can denote it by that notation which I already introduced as a 2-norm. But suppose we didn't know that, well, just use that notation. What is nice about this expression? Well, doing the calculation with the parallelogram here, you can check that it is the area of the parallelogram. It is the area of the parallelogram. Why? Because from this, I can, for example, I do this. I project it orthogonally, and I get this y minus something, say alpha x. Okay, I get this vector y minus alpha x. So the determinant is the same as if I do that. Well, call it y prime. So I get so I subtract alpha times the first row, then I get y prime, and here I get y prime too. Sorry. And the original determinant has the same value as this determinant. I don't take the square root at the moment. Okay, so I get this, and then I can also subtract minus alpha times the first column. Minus alpha, so the original determinant is equal to this. And if I keep the first column, and then I subtract alpha times the first column from the second column, then I get this y prime now. Y prime. Okay. And this is 0, that's 0, so I get 0, 0, and this is y prime, y prime. So this is exactly the area, the square of the area of the parallelogram. Okay? So the length of the base times the height, both square. Okay, so when you take the square root, then you get exactly the area. So this is the area of the parallelogram spanned by x and y. And as the area of the parallelogram of x and y, you can check the four properties easily, of course. We call this two norm the standard two norm on x, but then I didn't tell you the truth to check all the properties easily. Actually, the properties is always the most difficult one, right? Even for the norm. So now we claim that this is a two norm. The first property is easy, second property is easy, the third property is easy, but then the triangle inequality. How do we prove the triangle inequality? Okay, how do we verify the triangle inequality? And that comes the two inner product. So we define this determinant and we denote it by that notation. Later on we will call it, I already called it that two inner product. You can check the property easily using the property of determinants and of course the property of inner products, the inner product itself. Okay? And then if x is equal to y, then we get the two norm square. So if we take the square root, then we get the two norm, and that is the standard two norm. And in the next slide, I will show that of course we will have Cauchy-Schwarz inequality for this two inner product, and using the Cauchy-Schwarz inequality for this two inner product, we prove the triangle inequality for the two norm. So I don't show all the computations here, but the idea is with this two inner product, we can. I think I will write the Cauchy-Schwarz inequality. I have written the Cauchy-Schwarz inequality on the next slides, and then from that Cauchy-Schwarz inequality, the triangle inequality for the two norm follows. I make a little note here. Actually, I add this this morning that if one can use this notation instead of that notation. It's a bit different, okay? But z appears on the left and also on the right, and I put the vertical line there. Instead of this, one can actually use. So one has actually a function of 4 vectors, and in general one can have that all different x, y, u, and v, and one has this determinant. I didn't check the references, but this morning I just put this name quickly, general two inner product. But actually someone has done this in 2000 something. So, and we will encounter this again later when we talk about angle between two subspaces more generally. Okay? Now, to prove the triangle inequality for the two norm, it suffices to prove the Cauchy-Schwarz inequality for the two inner product, which looks like that. And again, this inequality may be rewritten as a determinantal inequality. This time each entry is a two inner product of three vectors: x and z, x, y, and z, y, x, and z, y, and z. So this is what we have to prove. But this is again easy. You just do this trick. Alpha and beta will go in the first two vectors, and then the first property of the two inner product says that the expression should be non-negative. Okay? So you will get this. So I have gone from norm, from inner product, I have a norm, and then I play around with the triangle inequality. I come with the determinantal inequality, and the matrix is interesting. The matrix, and I call this something, and that thing is actually a two norm. But then I want to prove the triangle inequality for this. I come with two inner product, and then I got the triangle inequality. First, if we continue the pattern, this Cauchy-Schwarz inequality, remember how we get the determinantal inequality. Remember how we get from this. This is equivalent to okay. Now we have this Cauchy-Schwarz inequality for the two inner product spaces. Doing some computation, this is equivalent to this determinantal inequality also. So we have now a determinant of 3 by 3 matrix whose entries are inner products of x, y, and z. All combinations x and x, x and y, and x and z, x and z, y and x, and so on. Which again clearly holds because the matrix is positive semi-derivative. You do the same thing here, then you get alpha x plus beta y plus gamma z, inner product with itself, which is of course non-negative. And we see also that the equality holds if and only if the three vectors are linearly dependent. Okay? So, now we have a 3 by 3 we have a determinant of 3 by 3 matrix. And again, we use the geometric interpretation. What it is? Well, if the determinant of the 2 by 2 matrix is area, then this must be volume. Volume of what? Volume of parallel pipe spanned by x, y, and z or z. So imagine this. The volume of a 3-dimensional parallel pipe. Okay? Of course, it's non-negative. And if you do the elementary row operation, you can prove that this determinant is equal to the length times width. The width is obtained by projecting y onto x, and then times the height. The height is obtained by projecting z on the base spanned by x and y. Okay, that's high school. So length times width times height, and it will be 0 if the three vectors are linearly dependent, meaning they don't build a three-dimensional thing, but maybe two-dimensional or even one-dimensional. So it has no volume. Okay, so to have a positive volume, they have to be linearly independent. And then the story goes on. How do we, if I call this trinom, how do we prove the triangle inequality for the trinom? Then I create the three inner product space, the three inner products, and I check the Cauchy-Schwarz inequality, I got it, and then I got the triangle inequality for the trinom. And then from the Cauchy-Schwarz inequality, I look at it again, and I got a determinantal inequality now with 4x4 matrix, and so on. Okay, nice story. Before moving on to the definition of n norms and inner products, let me note that related to the Cauchy-Schwarz inequality, this expression, this ratio, is nothing but the cosine of the angle between the parallelogram spanned by x and z and the parallelogram spanned by y and z. How do we draw that? Okay, so that is z. Z is like, now this notation is actually nice. If you remember, I offer an alternative notation. So z is like common or intersection between two parallelograms. So I have x and z, I have a parallelogram here, and I have y, I have also a parallelogram there. Now the angle between these two parallelogram is actually that. The cosine of the angle is this. Okay? I will come back to that when we discuss the angle between two subspaces. But these two subspaces are special. They have one common factor. Yeah? So in general, the Z here, you can have U there and V there. So the two subspaces do not have common factors. So the intersection is only 0. How do we compute the angle? Okay. So we will discuss that in the 4th and 5th lectures. So I have mentioned this, that this function defines a trinom, and we call this the standard trinom, which represents the volume of the parallelogram spanned by x, y, and z. Since this is a lecture, any question from the student, perhaps? Okay. If not, then I will move on. Actually, I didn't prepare so many slides as with my first lecture. So, but now let me give the definition of what an norm is. Okay, so X now is a real vector space of dimension D, which is at least equal to n. If it is less than n, then we don't. Then the first property says that then the value is always 0. So there is nothing to discuss. Okay, so at least the dimension should be n, meaning that we are talking we can talk about n-dimensional things at least. So this mapping on x raised to the power of n, x times x n times, satisfying the four properties. The first one always says that that the expression is equal to 0 if the vectors are linearly dependent. Okay? So if the vectors are linearly dependent, then we don't have an n-dimensional thing, but something less. Something less in n-dimensional has 0 volume. Okay? Like a plane in 3-dimensional space has 0 volume, or a line in 3-dimensional space has 0 volume. And second one, the value is invariant under permutation. Okay. The third one says if 1h is multiplied by alpha, then the volume is modulus alpha times the original volume. Alpha can be negative. Okay. If alpha is -1, for example, you just flip the thing upside down, or to the left, or to the right. Okay. And the fourth one is the triangular inequality. So if 1h is the sum of two vectors, then the volume will be less than the sum of the two parallel pipes. One is spanned by the first one with all the other vectors the same, and the sum of and the volume of the second one, x1, and then the same vectors x2 up to xn. Okay, so this function is called an norm, and the pair is called a norm space. Galler wrote this in 3 consecutive papers in 1969 and 1970. So the first 2 papers appear in the same volume, 40. Okay. And then in combining with the n norm, we have the n inner product. Now the dimension should be at least n plus 1. So otherwise we don't have the angle. If, for example, we have 2 inner product, but the dimension is 2, then we cannot have this picture, right? So the angle is always 0. So dimension should be more than n, at least n plus 1. And this mapping, the first 2 related to the property of the first 2 property of n norm. And then the third one, remember the notation, we use comma for between the first 2 vectors and then the vertical line, and then all the remaining vectors on the right, x2 up to xn, they have different roles with the first 2 vectors. So this function is bilinear with respect to the first 2 vectors, but not with respect to other vectors. Okay. So the other vectors x2 up to xn is like this z. But now imagine there are n minus 1 vectors in place of z. Okay? So this is hard to imagine. Imagine we are in R4. Imagine we are in R4, and then we have 2 parallel pipe with common plane, something like that, common plane. So the intersection is two-dimensional. Okay. So here the x2 up to xn plays same role as z, and the first two vector x0 and x1 plays the same role as x and y. So the function is bilinear in the first two vectors. But now the second property says that if the first two vectors are the same, then imagine we are having n norm, x1, x2 up to xn. Then the n norm is invariant with respect under permutation. Okay, so for example, x2 now can move to but as pair. Okay. So this expression is the same as that expression for any permutation I1 up to In of this sequence 1 to n. So for example, xn. So for example, this will be equal to x2. I should write another vector, just x3. Okay, so x2 and x1 exchange position. The third property, permutation between the two vectors on the left, and the fourth property, you can multiply by scalar, and then the fifth property. So the fourth property and fifth property are linear properties of the n linear products. And the Cauchy-Schwarz inequality you can easily prove because basically you can sort of forget about x2 up to xn. You just deal with x0 and x1. They are the function is bilinear with respect to these two vectors, and so you can prove it easily. You can do this thing. Okay, you can do this thing, and then you use the first property. So it's the same. It's the same same story that we have here. So just replace this with the candidate products. And as a corollary of this Cauchy-Schwarz inequality, we have that the square root of this expression. Now here x0 is equal to x1, so here we only have x1 up to xn. So this expression defines a norm, an n norm, sorry, on x. Now, are there examples? Yes, of course. The first thing is if x is a linear product space, so if x is equipped with a linear product, then on x we also have an n linear product, which I call standard n linear product. And we also have the standard n norm. Okay? So the n linear product is given by this formula. So if you look at x0 here, x0 appears in the first row. Okay? And x1 appears only in the first column. So x0 first row, x1 first column, and all the others x2 up to xn. Especially this submatrix consists only x2 up to xn. And if you forget the first row and first column, you recognize that submatrix as gram matrix formed by x2 up to xn. So for example, if x0 is orthogonal to x2 up to xn, then all this is 0. So this will be the volume of the n-1 dimensional parallel pipe, and then times this. Okay. Geometric interpretation the same as that, except that now Z is replaced by n-1 dimensional parallel pipe. The ratio, yeah, okay, I take the square root already. This is the cosine of the angle between the parallel pipe spanned by, so the first one, parallel pipe spanned by x0, x2, x3, and so on up to xn. And then the second one, the parallel pipe spanned by x1, x2, x3, and so on up to xn. So the two parallel pipes have common intersection of n-1 dimensional, of n-1 dimension. Okay? Later we will come back to this discussion when we talk about angle between two subspaces. So this is a special case when of angle between two subspaces. Now, of course, you're not happy with that. I mean, you already have an inner product. Why do we have to have something else? But I can make up stories, of course. I mean, in real life, we have many types of instruments, measuring instruments. We have ruler, we have something else. So, for example, if we know how to compute length, can we compute area? Yes, perhaps you say, but not easy, right? I mean, sometimes, like parallelogram, you have to do something first. I mean, you don't compute the area directly. So 2norm is like your equipment to measure area, knowing something about the factors involved in the area. On a norm space, so for example, we know how to compute length. How do we compute volume? Quickly, right? We don't want to do perhaps projection and so on. So we have this formula of n norm. Of course, this is not operational either, but this formula is an n norm. This is in the Gallner's paper, maybe the 1960s something. The idea is to use the dual of x, consisting, you've taken functional analysis course, right? Consisting of all bounded linear functional boundaries. So, if you check the property of a norm, they will be satisfied by this expression. Of course, for you, you have to remember in the simplest case. In the simplest case, this is hang on, we don't have that. We have this, right? So F is in the duals. But in inner product space, if X is an inner product space, then in an inner product space, you know that this is true. Y is less than 1. Is that correct? By Cauchy-Schwarz, you know it is less than, well, of course, it is a little bit upset. You have no more idea. Call it, for example, you have this, and then you define this by this, and then you would define another norm by this. They are actually the same, okay? Because by Cauchy-Schwarz inequality, you know that this is the absolute value. If this is real, so this is less than x times norm y, but norm of y is less than 1, so less than this. And then the supremum is attained by taking y is equal to okay. So I take in it this vector, then this is equal to norm x. So the supremum is actually, so I'm saying that this norm is actually the same as the original norm. Okay, for the basic property of functional analysis, I assume actually that you already know. So that is the idea behind this formula. Use the dual. The space that we know what the dual is of course the space of the sum of the sequences, and the Galler formula will be the same as this. So the functional is identified by a sequence also in LP prime. Okay? The dual of LP is LP prime. P prime is the dual exponent of P, meaning 1 over P. So on LP we have P prime, 1 over P prime plus 1 over P equals to 1. So LP prime is LP dual. LP dual is LP prime. F1 computed at x1 is given by this sum and so on. So we have here the sum of the products of x1 and x1 and so on. Here x1 and yn, and there we have the product of x1 and y1, and here x1. xn and yn. There is another norm on LP. So this is for you who wants to have an example of an n-norm. This expression also satisfies the n-norm properties. I wrote a paper about this in 2001, and of course you might ask, how did I get the idea? For p equals to 2, L2 is an inner product space, and the dual of L2 is itself, so you can and you know the sum is actually the inner product, and then the determinant like this, the sum inside, you can take the sum outside, take it out, and then you get double sum. If it is a 2 norm, you get double sum. And then you also consider the order, which one you take out first. So you permute, and then you get, in that case, you get 2 times. That's why we get 1 over n factorial there, because the permutation factor there. So if p is equal to 2, this is exactly the determinant of the gram matrix, if p is equal to 2. So for p equals 2, from the determinant of the gram matrix, you can get this exactly. But of course, we know on L2 we have the norm, sum of everything squared, and on LP we have the norm, sum of everything to the power of p, and then the sum is raised to the power of 1 over p. Now we can do the same for this determinant. So now we have n vectors, we have this determinant, and I imagine that as the, how to write that? Maybe I will give illustration for 2 norm. Okay, I will give illustration for 2 norm. So this is x1. Imagine this is x1 and x2. I have x21, x22, x23, and so on. Now, when we compute the norm of a sequence in LP, we just take each absolute value of each term, and then we sum them. Okay? Now, we want to this. Now, how do we define it? The idea is the same. We take any two columns here, for example, this and that, and then I get this. So think of this as the area of the original parallelogram projected on the second axis and the fourth axis. I get one area, and then I raise it to the power of p. Okay, I have to take the absolute value. And I get many of these, so that's why I get this. And then I replace this by, if there are 2, then I can just say x1j, sorry, maybe j and k. Or k1 and k, j and k, okay. x1, j, x1k, x2j, x2k, absolute value raised to the power of p, and then I take 1 over 2. Maybe that's not really important, but to make it equal to the area of the parallelogram when p is equal to 2, I have to have 1 over 2 here. So this is the 2 norm, but now with respect to the power of p. I think I'm almost done. My time is. So I just make comments here that the 2 norms are equivalent. What do we mean by that? Well, it's similar to the equivalence between norms. Now we have also equivalence between 2 norms. Sorry, 2 n norms. And that means there are constants a and b, positive, such that this holds. And these are written by myself with my master student at the time, 2010, and also 3 years later with my other student. So we got stronger result. The first one used sequential equivalence. The second one we really obtained the value of a and b. We obtained the value of a and b. I think that's the last slide. So tomorrow I will enter the topology. So I will discuss sequences, completeness, and maybe fixed point theorem on n-norm spaces. Thank you for your attention.